This video relates to the section in Chapter F1 of the Common Core where we're looking at idea number 2 for investigations. This involves an experiment that is videoed and from which we have acquired some data. These data are entered here. The times are recorded by freeze framing the video, and we've got some pairs of times and displacements. The displacements are measured from the center point, which is 2 centimeters to the left of the clock, a vertical line on the grid. So a displacement of 1 means that the pointer is 1 centimeter to the right of this 0 line, and this displacement of negative 3.9 means a bit less than 4 centimeters to the left. We have also chosen, because it's very difficult to start the timer and the experiment simultaneously, to just start the timer and choose an arbitrary 0. This arbitrary 0 in our case is at 13.15, so every time elapsed is recorded as the time on the clock, which is over here, minus the 13.15, the arbitrary starting time. When it comes to analysing the data, Excel tends to work better if you have an evenly spaced time scale. So over here in columns F to H, what we've done is set up a time scale that goes up in 0.05. We've actually used a formula to do this, but that's not necessary. So this item of data here, which is 0.06 seconds and 5.8 displacement, has had to be recorded as 0.05, 5.8. This is the next data point and so on. It's best if you look at this graphically. So before getting the graph up, I've put in a draft model that is indicated by the figures given in the text. The formula here represents the model that's given in the text. So it is essentially A, which is the figure stored in E1. We're using absolute cell addresses here, which is the dollar signs, which means that when you copy this formula, the cell address is not updated, it is absolutely copied. N is in cell E2, again an absolute cell address, hence the dollar sign. Time is stored in cell F6. We want this to be updated when we copy it down the column, so no dollar sign here. And the left-right displacement, the parameter C, is stored in cell E3. So I will escape from that. What I've done is I've entered it once, as you do in spreadsheets, and copied it down. We want to show this graphically, so select everything. We'll select the column headings as well. This has a slight advantage that you'll see in a minute. I'm going to choose the scatter graph, which is a reasonable starting point quite frequently. So what we've got here, having selected the column headings, we're told here over on the right which is which. The data are the blue diamonds, and the model, the fitting model, is the set of these squares, the orange squares. As you can see, we're not too bad. Our initial guesses, based upon the arguments in the text, have not been too bad. I think the first thing we might notice is that the amplitude is going to be about right. So I'm not going to fiddle too much with 8, initially at least. The first thing that strikes me is that I think that the displacement is a bit out. I think it's all a bit to the left. So the first thing I will do is just tinker with this figure here. If I change it to 2, I make it worse. So think about your displacements and the discussions that you would have had and the learning you did when you were learning about trig graphs. This is what would happen. So I'm going to put it back to 0 because increasing it is in the wrong direction. I'm going to decrease it. Now that looks a lot better. Here we're not what's called out of phase at all. The reason it doesn't match here is that we need to adjust the period. 9.1 was a reasonable good guess, and the text gives the rationale behind making that guess. If I increase this, again, n and the period are inversely proportional. So an increase in n will reduce the period, and that's going to be wrong as well. So for argument's sake, I'm going to just pick a number. I'll pick 8.8, and we will alter it to that. The model's period has now increased, and the fit is somewhat better. I think I'm going to go another step and maybe try 8.6, and we will have a look. That's altogether better, and in fact that's not a bad fit at all. We've got a few ropey things, but this was a fairly rudimentary experiment, and I don't think that's too bad. So what I'm going to do is report that as the set of parameter values that I think best model the periodic part of this motion. The text will look further at modelling the exponential decay, because this does not carry on vibrating like this. The amplitude decreases, and we're going to use an exponential model to model that as well, and we will do that in the next section.